Okay, so what we're going to do this time is we're going to take a confidence interval, 95% confidence interval, and we're going to use the standard one you'd use for a normal distribution. So let's assume that I want to get a confidence interval for the population mean. And we're going to make it nice and easy and assume that I know the population standard deviation. And if you remember in previous courses, you've probably seen a formula for calculating that. But what we're going to do is we're going to show that this is actually a proper confidence interval. Okay, so let's go and have a look. So over here we have my theorem. We've got y1 up to yn at IID normal. They've got a population mean of mu and a variance, a population variance of sigma squared, and we're going to assume that sigma squared is known. And then if I take the usual thing, which is the sample mean minus z alpha on 2 sigma on root n, and I take the positive version that way, plus instead of minus, that is a 100 1 minus alpha % confidence interval for mu. Okay, so first of all, let's think about what we want to do. What we really want to do is we want to show that the probability that the random variable L, which is the lower bound, is less than mu, which is less than the upper bound, that probability would be 1 minus alpha. That's what I want to show. Because that's the definition of a 1 minus alpha 100% confidence interval. Now, there's a couple of things to notice. There's a subtlety here. We're used to the bit in the middle being the random variable. We're used to that being the thing that has a probability. But that's not the case with confidence intervals. In confidence intervals, it's the L and the U that have the randomness associated with it. Okay, so let's see how we're going to do. What we're going to do is we're going to start by writing our statement. So we've got y bar minus z alpha on 2 sigma on root n is less than our parameter, which is mu, which is less than the positive version, alpha on 2 sigma on root n. And what I'm going to do is I'm going to slowly manipulate this. So that's our starting point. The next thing we're going to do, let me just shove this iPad across, that's good. I'm going to take the sample mean off all parts of the inequality. So I'm going to write this as z alpha on 2 sigma on root n is less than mu minus y bar, which is less than z alpha on 2 sigma on root n. Cool. Next, I'm going to divide by sigma on root n. Now, you have to be careful when you multiply or divide either side of an inequality. You just got to be cautious. And you can ask yourself, is it positive or negative? Well, sigma is always greater than 0. N is always greater than 0, the square root. So the sigma on the square root of n, so let me just write this down. Sigma on the square root of n is always greater than 0. So I don't have to change the inequality. What that means is I can say this is the same as minus z alpha on 2 is less than mu minus y bar sigma on root n, which is less than z alpha on 2. Now, this in the middle looks familiar, but not quite. We're used to seeing y bar minus mu, and it's not that. So what I'm going to do, I'm going to times every part of this inequality by minus 1. So I've got the probability. I've now, if I times minus z alpha on 2 by minus 1, I get z alpha on 2. I'll get y minus mu on sigma on root n. And I've got z alpha on 2 minus. But remember I said when you multiply, you've got to be very careful. If you multiply by a positive number, the inequalities stay the same. But if you multiply by a negative number, you have to change the inequality. So this now becomes a greater than, and this becomes a greater than. Not convinced? Well, 1 is less than 2, but minus 1 is greater than minus 2. There's my beautiful example of what I just did. So I can rewrite this as the probability that minus z alpha on 2 is less than y bar minus mu sigma on root n, which is less than z alpha on 2. So this is a number, this is a number, and here's my random variable. Well, we know that random variable, we recognize it by now. We know that this is a normal 0, 1. So let's work out the probability. Well, let's draw our normal distribution. Here's our 0. Here's our minus z alpha on 2. Here is our z alpha on 2. And this is designed that the area to the left of it, will be alpha on 2. And this is also designed such the area greater than it is alpha on 2. So this area here, the probability that we actually want, is 1 minus alpha on 2 minus alpha on 2, which is 1 minus alpha, and that's what we want. We've chosen these random variables, which were these big things up here. So we chose this random variable, which is our L, and this random variable, which is our U. And we've shown that the probability they lie either side of mu is 1 minus alpha. So there you have it. A classic example of showing that this formula I gave you is actually a 1 minus alpha 100% confidence interval. Booyah. Thank you very much. See you next time.